Have you ever thought about what happens when the inside of a massive industrial furnace just gives up? Well, it's not just an equipment problem. For a material scientist, it's a crime scene. So today, we're going to put on our detective hats and dive deep into the world of refractory forensics to figure out exactly why these super tough furnace linings fail. So here's our game plan. First, we'll survey the scene of the crime to understand the environment. Then, we'll round up the usual suspects, the common causes of failure. After that, it's off to the forensics lab to see how we analyze the evidence. And finally, we'll talk crime prevention, how to stop these failures before they even start. All right, let's get our bearings. We're stepping into a world of absolutely extreme conditions. We're talking crushing pressure, corrosive chemicals, and, of course, mind-boggling heat. This is a place where even the most durable materials can be pushed to their breaking point. And at the heart of it all, you've got these things called refractory materials. You can think of them as the unsung heroes of pretty much all heavy industry. The official definition from ASTM C71 says they're non-metallic materials built to handle insane temperatures. We're talking over 1,000 degrees Celsius. Plus all the chemical and physical abuse that goes on inside a furnace. They are literally the only thing containing the inferno. So when one of these linings does fail, who or what is to blame? Well, it's time to line up the usual suspects. These are the most common culprits that our refractory detectives find out there in the field. First up, meet our prime suspect, the brute force attacker, thermal and mechanical stress. This one isn't subtle. It uses pure, overwhelming physical force, from crazy temperature swings or just straight-up mechanical pressure to literally rip the refractory apart. And its favorite weapon? Something called thermal shock. Imagine heating something up red hot and then dousing it with cold water. That massive, rapid temperature change creates enormous stress inside the material. It can't expand or contract fast enough, and crack, it just breaks. Now, when our detectives show up at the scene, the evidence for this kind of attack, which we call spalling, is usually pretty obvious. They'll find telltale clues everywhere. Big visible cracks, chunks of material that have just broken off, or even entire layers that have peeled away from the wall. It's a clear case of structural failure. Okay, our next suspect is a whole different breed. This one is the silent assassin, chemical attack. It doesn't use brute force. Instead, it's a slow, sneaky failure caused by reactions with the very stuff inside the furnace, like molten slag or nasty corrosive gases. And this suspect has two favorite methods. The first is corrosion. This is a purely chemical attack, where molten slag just sits there and slowly dissolves the refractory, kind of like sugar in hot coffee. The other method is erosion, which is more physical. That's when moving slag acts like liquid sandpaper, physically scouring and washing the material away. Two different approaches, same devastating result. Now, the clues left behind by a chemical attack are way more subtle. You might find this glassy glaze layer on the surface, but sometimes the attack is even more clever. Carbon monoxide gas can actually sneak into the pores of the brick and cause it to crumble from the inside. Or, even worse, chemical reactions can create new liquids that have a super low melting point, basically poisoning and weakening the refractory structure from within. And our final suspect is the slow burn. This is the one that takes its time. High temperature creep. This isn't a sudden, violent failure. No, this is a gradual, relentless process where the material slowly deforms over a very long time. So what's actually happening here? Well, on a microscopic level, under constant heat and pressure, the material's internal structure just starts to shift. The tiny grains that make it up begin to slide past each other. Over months or years, the refractory permanently loses its shape and strength. It's almost like the material just gets tired of holding the load and starts to sag. Okay, we've identified our top 3 suspects. Now it's time to take the evidence we've collected from the crime scene and get it back to the lab. This is where we use some serious science to prove beyond a doubt who the real culprit is. And in the lab, our team has a whole toolkit at their disposal. They'll start with the basics, like checking bulk density and porosity, which gives them a picture of the material's overall quality. Then they might do a cold crushing strength test to see how tough it is at room temperature. To test our silent assassin, they'll run slag corrosion tests. But you know, the real workhorse, the test that often cracks the case wide open, is refractoriness under load, or RUL, which shows us how the material really behaves when things get hot.
So this brings up a really important question. What's the secret weakness? The hidden link that makes a strong refractory suddenly vulnerable to a chemical attack. Well, the answer isn't on the surface. It's deep inside its structure.
It all comes down to something called porosity. It's pretty simple, really. If a material has low porosity, it means there are very few tiny open pores for that nasty slag to creep into, so it's naturally more resistant. But a material with high porosity, it's basically like a sponge. It just soaks up that destructive slag, letting it penetrate deep inside, which leads to way faster corrosion and ultimately failure. Let's circle back to that really important test I mentioned, refractoriness under load, the RUL test. This is so critical because it doesn't just test how hot the material can get before it melts. No, it simulates what's actually happening inside a furnace. It hits the material with intense heat and constant pressure at the exact same time. And here it is. This is the actual machine. A sample of the refractory gets put inside, a weight applies constant pressure from the top, and then the furnace starts cranking up the heat. This is how you truly put the material through its paces and see what it's really made of under real-world stress. So what does this test give us? The RUL results provide the smoking gun. It tells our detective the exact temperature at which that material starts to soften and give way under pressure. This is the proof. It tells you for sure whether the right material was chosen for the operating conditions in the first place. Okay, so we've identified our culprits, we've analyzed the evidence, and we've closed the case. But the job's not done. The most important part of any investigation is making sure this crime doesn't happen again. So let's talk about crime prevention. And really, preventing these failures boil down to three key things. First, you have to start right, with proper installation and a very slow, controlled dryout to avoid early stress. Second, to stop our brute force attacker, you have to control your operations to minimize those thermal shocks. And third, and this is maybe the most important, you have to learn from every single crime scene by doing a systematic failure analysis every time. And that right there is the big takeaway. A systematic post-mortem analysis is absolutely the key. Every failure is a lesson packed with data. By doing a full forensic investigation each time, engineers get the critical information they need to make smarter choices on materials, on installation, on operations, and finally break that cycle of failure. Which leaves us with one last big question to chew on. When a furnace lining fails, is it because the material wasn't good enough for the process, or was the process just too brutal for the material? As our investigation shows, the truth is almost always found somewhere in the middle.